Thank you so much. So it's my fourth talk here. I apologize for hearing my voice too much. I'll try to go through sections of studies, and it would be great to ask questions at the end of those sections so we can get through a couple of things, if that's okay. All right. Most of my research, I've come to realize, has to do with memory and search. Memory mostly being associated with the hippocampus in the brain, and search mostly being associated with pretty much everywhere in the brain, especially the prefrontal cortex and the hippocampus. However, I do memory and search both in individual and collective intelligence. And I thought that today I'll start with parts that I haven't talked to you guys about, which is the topology of collective intelligence. If this part was not the part that you are most excited about, we can skip through it quickly, but hopefully you will find it interesting. Another thing is that my research is always trying to computationally model aspects of cognition that I'm interested in, both in terms of individual and collective intelligence, so you'll see a lot of different kinds of computational approaches. Usually, and if you're interested in these approaches with successor representations, multi-scale predictive representations in the brain, you can take a look at these different references, and you can also look at the other talks that I gave, but I'm happy to talk about these if anybody was interested. Okay, so in addition to individual intelligence, the majority of human culture is rooted in sharing models, skills, and memories to guide our behavior. This could be in the domain of math, it could be in the domain of music, it could be in the domain of architecture. I specifically put these particular patterns that you would find in mosques all across the Middle East because the mathematics of it was not formalized until centuries after these things were very commonly made. And there was a mystery of how this kind of equations were passed on, and it turned out it was in the weights of Persian poetry that they were passing on to people who didn't even read, but they could actually reconstruct these on the basis of those passing on. So there are many different interesting ways that cultures pass on information. I was very interested in collective cognition in general, and I found some of my diaries from before, and I saw that I'm mapping like dynamics of lab meeting, eye contacts, or my mom's side of family with graphs. As you can see, I also do the same approach when I'm thinking about how we search things in the brain or how memories are constructed. And obviously, there is a long history from cybernetics to various social science perspectives that use graphs and mathematics in understanding both individual and collective intelligence using various graph theoretic approaches. So it is in the spirit of all these traditions that I'm going to start by talking about how social network topology shapes collective cognition and innovation. You can tell that I've pieced together different talks because in this middle slide, you still see my name and association. Okay, I will talk to you about a couple of individual studies, but if you would like to read a bigger review, this is a paper that I wrote in 2021, reviewing various aspects of these, and these are some other papers. I'm not going to be able to talk about all of them. The broad idea is that there is a collective architecture of different kinds of intelligences, in the sense that the same number of people would behave optimally for different kinds of tasks depending on their social structure. The same way that different brains or different neurons, when they're organized differently, the same number of neurons when organized differently with different architectures, they're going to be optimal for potentially different kinds of tasks. So first, let's take a look at how graph structures of conversational networks can shape collective memories. This is a study that we did. Okay, so just to describe what you will see in the studies that will follow is particular individuals as nodes. You will have certain relationships. You will have different shapes of graphs, and I'll describe them as we go. Broadly, the general thing, and this was a PNAS paper we had in 2016, was that we would have individuals come to the lab and study alone. And this is a memory task. They would first study 4 categories, and each category had 4 items, so 16 total. Then they will take a test alone, a memory test, before having conversations with others. And because it's a 16-item vector of whether they got something wrong or right, every person's pre-conversational memory would be a 16-item vector, basically. Very simple. And then there is a number of conversations. And after that number of conversations, each of them for just 3 minutes, and there is 10 people in each group, and each person has 3 conversations. A chat pops up. They don't know they're a part of group. They don't know how many. It's just that there's some chat popping up. They have some conversations, and then they take the test again afterwards. So you have another 16-item memory vector after the conversations. The fun part starts when you can compare the correlations of these memory vectors before and after the conversations within and across individuals in different shapes of networks. So the two networks that the two kind of social architectures that we compared to each other had the same number of nodes, both of them 10, and the same number of communication or conversation edges. The only difference is in the relationship between edges 2, 1, 9, and 10. So in the clustered condition, you see that instead of 2 and 10 and 1 and 9, you have 1 and 2 and 10 and 9 connected to each other. And only this small change leads to a clustered network with a diameter of 5, which is the longest, shortest path between any two, versus this other case where just with changing these 2 nodes over here to these guys, you can see that we have all of a sudden a better connected network with only diameter of 3. So we had a couple of predictions, but I'm just going to ask you something. So do you think, how many people think conversations in the clustered conditions versus the non-clustered conditions are going to lead to more convergence in the memories after the conversations? So before the conversations, we all had some distances in our memory vectors. After the conversations, we got a lot closer. Which network do you think that happens, which is a mnemonic conversion or memory convergence of different people? In the clustered or non-clustered? How many people say clustered? How many people say non-clustered? The majority is correct. Our predictions was that in networks with fewer clusters, which is a smaller diameter, we will have a higher convergence. And for those who raised their hands for the clustered one is better for hierarchical problem solving and search, as you will see. So remember, my research is about memory and search. This one is better for memory. The clustered is better for search. All right, among members with smaller degrees of separation, we would expect a higher convergence, and we would expect that some principles can help us predict the content. So here's our prediction. On the basis of on each of these, you will see each of the nodes on the rows, and on the columns, you also see the nodes. And the color corresponds to what degree of separation they had. So obviously, the diagonal is 0, and the highest degree of separation you have here is 5 because of diameter of this network. The highest degree of separation here is 3 because the diameter of this network is smaller. And the prediction is that the bigger the difference, the lower the convergence, basically. And the way that we define are very, very simple rules, which is mnemonic similarity, which is how these vectors that we talked about, for instance, for person 5 and person 6, you can basically take a look at how the number of the items that they remembered in common is similar. Mnemonic convergence would be how the mnemonic similarity of all ij nodes and pairs on average would be. And mnemonic alignment would be how their basically mnemonic similarity post conversations differs from before the conversations. And so these are very simple tricks to figure this out. So this is the results as the majority predicted. Generally, there is a much higher convergence in the non-clustered network, and this difference is significant in terms of the difference between the pre and post. And interestingly, this distance between this degree of separation predicts how much pre-post similar or post minus pre similarity you get. So how much closer you become to each other is very much related to how close you are. The higher your degree of separation, the less close you become to each other. Okay, I think in the interest of time, I might skip this part or say it very quickly, that then you can use some principles of retrieval-induced forgetting, which is if you have different things in your memory, in the ones that are connected to each other, you keep reinforcing one, after these repetitions are done, you have a little bit of a less accessibility of the item that was not practiced but was related, but no difference in the ones that were completely irrelevant. And so when we applied those principles to the items that people remembered, memory score before the conversation, and then we compared, we looked at the conversations, we coded their conversations in terms of which items from the categories were reinforced and which were downgraded and which didn't matter because it was in a different category and wasn't mentioned, you get a cumulative score, and that cumulative score allows us to predict which items in the collective memory of that collective is going to become more prominent or is going to become forgotten, which was a little awkward. It felt like we were being the NSA of our subjects because we were looking at their dialogues and predicting what would be their collective memory. All right, so more convergence where geodesic distance is smaller, more convergence in non-clustered networks. Something that I'm not going to talk about a lot, but I just put it here because of Jacob, is that we used simulations using spread of activation in networks, using, in fact, word2vec to construct our sort of fake memory, our computational memory. And by applying these principles of retrieval-induced forgetting, which is also called non-monotonic plasticity hypothesis, we could actually not only replicate these results in modeling with very simple spread of activation principles using word2vec, we also could create forgetting attacks. Like we could decide what to keep showing someone so that they forget another concept. If anybody's interested in that, I'm happy to tell you guys a lot more about it. All right. Another thing, yeah.
What's non-monotonic plasticity?
Oh, it's related to the retrieval-induced forgetting that I mentioned. And so the idea is if you have no relationship to the memory that is being activated right now and reinforced right now, then nothing changes with you. If you have a small relationship to it, you will get a little deactivation. So the non-monotonic aspect is that it's not just that it increases some, it decreases the ones that are neighbors. Yeah, thanks. All right, so there is this idea that there would be bubbles. These studies, we did it in 2017, 18, so you could imagine which bubbles we were thinking about back then. And so we were interested in, okay, what if there is a fixed network? The shape of the network is fixed. What should be the temporal order in which people talk to each other if you want to converge or if you want to, for instance, be better at search, right? So again, collective memory. This was of interest, for instance, if you want to do interventions before elections. Should you do closer or should you start a lot earlier? And the way that we designed this one is very similar to what I showed you earlier. The network structure was the same. It was a 16-person network. There were 4 clusters here. The red edges that you see are bridge ties. They are bridging 2 different clusters to each other. And the black edges that you see are cluster ties. They are within clusters. So you can have a weak ties first condition, and you can have a strong ties first. Or you can think about the cluster ties as strong ties, and you can think of this sort of longer ones as weak ties. You can think about this as if, let's say, Jacob and I have a lot of friends in common, but let's say that, for instance, Dave and I have a very close relationship, but we don't have a lot of friends in common, which means that Dave and I would be weak ties, but Jacob and I would be strong ties. And the question here was, which group should talk first in order for the memory of the network to converge? What is the prediction? How many people think weak ties first in order to increase the convergence of memories? Okay. How many people think, okay, how many people weak ties first? I saw shy hands. Okay, good. How many people strong ties first? Shy hands. Okay. 1 confident hand and a couple of shy hands. So again, the majority was correct, which is not common. Usually people get this one wrong. It turns out that, and this is the structure of it, everybody comes individually, reads something, then they have these kinds of individual tests. Again, we get in this case, 30-item vector. And then in the bridge ties first condition, or weak ties first condition, what you get is first the bridge ties talk to each other, then you have 3 rounds of cluster ties. And in the bridge ties last condition, or the strong ties first condition, you have 3 rounds of cluster ties talking to each other. And then in the last round, the bridge ties talk to each other, and then you have a recall test at the end. And what you can see here is this is the pre and post. This is the difference that you get between the bridge ties first, which is the highest convergence, and weak ties first. What interesting thing you see here is that this is within the same cluster. Even convergence before and after within the same cluster is higher for the bridge ties first condition than the bridge ties last condition. So it doesn't matter that much for the distant clusters, but it definitely matters for both within cluster and neighboring cluster. Why is that? So we further analyzed, again, we NSA'd their conversations. And what we were focusing on this time was in the conversations they were having, in the multiple conversations, every person had 4 conversations, what was overlapping and what was different. So if you had overlapping items, then that means that you had more similar things you were talking about. But if you had diversity in the items, it meant that you were basically having different information. You were not just repeating the same information. What happens is that when bridge ties talk first, the diversity initially is high, and then the diversity starts to go down. But if the cluster ties talk first, the diversity initially is low, and then in the last one it goes up. And so if you compare the diversity of, and by the way, this diversity and overlap is measured for each cluster, which is the reason that you see here a difference from even round 1, right? So within every cluster, each of the clusters has 4 people. In the cluster ties first, only 4 people talk to each other for a while. After 3 rounds, each of them talks to a different person, so they kind of diverge from each other. In the other case, each of them has already talked to someone else, so by the time they start talking to each other, they are converging, they're bringing things together. So diversity is high first, which is why we got this result that initially is puzzling, which is why would people even within the same cluster converge more if the bridge ties talked first. So we thought this was a very cool thing. We had some very easy and fun mathematical games with it, which is very similar, again, for those familiar to the successor representation. And what you get here is a very simple equation with a recency term, so items that were recently kind of introduced, and a practice term, items that were repeated and across multiple of the conversations in these different paths in this conversational flow. And what you get is a nice kind of replication of the items. So, sort of. So it's like there's a higher baseline for the 0 here. All right, let me go to, OK, interim summary. Memories converge more in communication networks with small degree of separation and bridge ties share, and when bridge ties share information early on. And models combining structure of communication networks with memory principles can predict these things. I'll show you more related things to this. OK, so I mentioned that different network topologies serve different goals in humans and machines. And this could be that there are different topologies that are optimal for solving hierarchical problems, for innovation, to isolate a virus, to synchronize memories just before election, or to prevent mass spread of information, for instance. So what would be the kinds of social architectures for these kinds of approaches? There is this famous paper that I'm sure a lot of people here are familiar with by Derricks and Boyd. They had a kind of an little alchemy type task where there were a number of early elements. By combining some of them, you could get another element, and you could get another element here. And then based on the different trajectories, you could do 3 levels of innovation. They had the same the same size groups, one group, a number of groups, obviously, they did statistics on it, one group, and both groups had 6 people. In one group, everybody worked together on the problem. In the other group, people worked in clusters of 2. And halfway through the experiment, they shifted their group. So the second group had dynamic connectivity. The first group had full connectivity. The second group had a cheaper connectivity because there was fewer nodes or connections that was necessary, that was happening. The first group, it was always all-to-all. So a lot of information sharing was happening. And what you see here is that basically the group with partial connectivity or dynamic connectivity always did better in general in all of the different tasks. And actually for level 3, the only group that solved it was the partial connectivity group. We then replicated these results with groups of DQNs, just deep RL networks that were talking to each other. The way that we had them communicate with each other was very simple. They were simply sharing their replay buffer. So they would go around in the world, have experiences in Little Alchemy, which is very similar, as you can tell, to the Derricks and Boyd approach. And then once they had some experiences in intermittent intervals, they would share the contents of their buffers according to a particular structure or dynamics. Either it was in a full connectivity, we tried ring, we tried a number of different things, I'm not going to go into detail, or you had this kind of dynamic connectivity, just like I mentioned earlier, where you have only groups of two, and then they kind of exchange their groups. And yeah, the approach was very simple, a DQN networks where the replay buffer was being shared as a communication. Just to be very quick and get through things fast, I'll just say that if you had just one single path to success, all of the different networks that were not sharing, dynamic, fully connected, ring, and small world, all of them did equally. But if you had emerging path tasks, you had to make innovation in one path, another innovation in another path. And this relates to search and work that Peter Todd is also interested in. So you have one path and another path, and you have to merge the path towards innovation. Then what happens is that the dynamic network outperforms massively. When you have a best of 10 paths, so you need to try 10 different paths and see which one was better, then dynamic was still best, but ring was getting at least a little bit closer. But if you look overall, it turns out that dynamic connectivity, in spite of the fact that it's cheaper in terms of how the DQNs connected and communicated with each other, was actually the best solution. We also tried the same exact experiment in LLMs. So we had them try, again, obviously in this case, they didn't need to share replay buffer. They actually verbally talk to each other, so you can see the content of the conversation. Again, in the interest of time, I'm going to go very quickly over this. You can see that there is a difference in the inventory size, how many items in Little Alchemy they managed to get through, and also time steps towards coming up with valid combinations. In both cases, you see that the LLMs that talk to each other according to the dynamic connectivity did better than the group that was fully connected, even though the fully connected group is obviously a lot more expensive. Okay, yes, questions?
Can, nope, forward, the way.
Forward?
Yeah, just keep going this way. Yep, here. Do you know, this is super interesting, do you have an explanation for why you see this sort of saltational thing?
This?
Yeah.
So this is inventory size, and I don't want to say something without looking at the data, but in terms of innovations, you ought to suddenly come up with something that combines with a bunch of things, and that could be the reason. But I think it's a good question that we can further analyze. Yeah, absolutely. I did think I put this for you because I knew because of your interest in cultural accumulation. Interestingly, there are similar phenomena, I think, even in monkeys in terms of cultural accumulation. For them, it's with plant medicine and different families of, I don't know if it's chimps, because the monkeys was at the Oxford study. I think chimps were the first study. And different families would be storing the different things, the different plant medicine things. And they also found it in hunter-gatherers. So there is this idea of a dynamic network keeping this. And the way that they shared the knowledge was through mating. Basically, whoever made it, they shared the family's knowledge. It was very interesting. OK, so this is another Phil-Trans-B paper that I had. And this one was about what does it mean when we are looking at human-like AI or neuro-AI. I think when we are talking about comparing intelligences, it's extremely important to see what the goals are. The goals, this rubric that I'm proposing for it, is that your goal might be engineering, and that's totally a valid goal. In that case, you are not interested in explaining or understanding intelligence of the natural world. You might be interested in just building one. So the goal might be prediction and control rather than understanding. And those are different goals, however. I think we shouldn't confuse them. If the goal is to be neurally plausible, it doesn't mean you can't apply engineering methods in science and vice versa. It just means just different goals, different directions people care about. Neural plausibility, again, it can be a goal. You just want something that resembles some aspects of the brain. This can be a small circuit. This can be like a network connectivity. And then you have human-like behavior or cognition being your goal. There are many models that are very high on this one. They capture some aspect of human behavior, but they're not neurally plausible at all because they're, let's say, probabilistic models. They make a lot of assumptions. They're wonderful for behavior, but not so great for neuron. There are some aspects that are over here, which are neurally plausible. However, they're not very good when it comes to explaining actual behavior. And one of the examples of it I have here is related to an example that came up in 2 talks earlier, which is the idea of adversarial examples. Convolutional neural networks, or CNNs, here's some kind of a history. It's not a complete history, but some kind of a history of it. They've been around for a while. They were inspired by vertebrate visual nervous systems. It turns out that even though they're good at doing certain kinds of classifications and they have some similarities to the different layers from V1 to MT of monkey and human data, the interesting aspect of them is that, as you can see here, this is a banana, classified as a banana. But if you put this tiny little patch next to it, all of a sudden it becomes a toaster. This is obviously completely crazy. And this is one of the cases of adversarial examples. Another example that was shown in one of the talks is you have this item being panda. You add this noise. The noisy item, to the human eye, I cannot tell the difference between the two at all. All of a sudden becomes a gibbon. So it's very interesting to see something that was completely accepted for a decade or more as the kind of model of human vision. And it's still one of the models that is up there. But it is so easily failing. There was some work recently, and there are some tricks you can do with creating some kind of a foveal-based training. Folks at MIT have done this in Poggio Lab. However, as Dan Yamin said in his talk, there is no clear solution other than really training adversarially, which is not the way humans train. So this kind of makes CNNs, even though they are high on the kind of neural plausibility, it makes them low on the human behavior. So I want you guys to keep this in mind when we are thinking about different models of intelligence. Which direction is the goal, and is it multidimensional? How important is one direction versus the other? With that, I will go now to a little bit of gaming AI and generative AI. And how much time do I have?
You have 22 minutes.
Okay. So when we are talking about human-like agents and neuro AI, it's important that we don't use the terms just interchangeably and carelessly and just throw them out there. It's important that we understand what is the goal of the terms that we are using, what are the priorities, what is the criteria for success. If your goal is to have something that's neurally plausible and captures behavior, that's a very high standard. You are going to do a lot more work. You have to combine a lot of disciplines. And your failure is definitely likely, and you will have to take a longer time in your career and publish papers. And if you compare that to an engineer that can publish a lot of papers in a certain area, it's important to keep that in mind, I think, when you're looking at your work and if you're deciding your future for grad students who have been talking to me during this time. And also, the success in one or two direction, as you saw in the case of CNNs, does not guarantee that you have success in another direction. You could have something that was very much based on looking like some circuits in the brain, but its behavior is wacky. You can have something that looks great for behavior, but doesn't predict anything neurally. And so it's important to remember explanation and understanding are not the same as prediction and control. And I think this is something that should come up a lot. Now, with all of that, I'm going to show some work on human-like evaluating whether agents, transformer agents in this case, trained on large-scale amounts of game data, show cooperation, competition, exploration, and exploitation similarly to humans. So this is an example of evaluation now. We talked a little bit about social architectures. I'll talk to you about the architecture of this one. But I think my main goal in here is to show how something that looks like it should do great would fail if you analyze it in a different way. OK, so we have Bleeding Edge, which is a game that was developed by Ninja Theory. It is a 4x4 game, so you have two groups. Each group has 4 people in it. So as you can tell, very complex game. In this game, the objective is to take some seeds, deposit it in some places, make sure you keep that deposit and don't lose it to the other team. And there is fight behavior. There's different kinds of characters, as you can see. Some of them are healers. They can shoot healing vibes at each other. Some of them are fight characters. So depending on the character you're playing, the behavior is different. And this is very much thanks to these amazing interns that I had at Microsoft Research, especially Sue Sharma, who was there recently. All right, let me see if I can play this so you can get an idea of how crazy the game is.
Here we go.
Nice. Eat that. All right, Jane, your super is full.
Yay!
Just FYI.
All right, okay, I'm gonna.
I'm dizzy and confused.
Oh,
wow. Oh my god, I'm gonna hit my trade again. Do a dance, Jane.
Do a dance. There we go.
There it is.
You see my dance, Mike?
Yeah, I'm accompanying you on the axe.
Evade, evade, evade. Right.
And remember your evade button.
I'm very slowly learning to
Wow, I got owned. Got absolutely owned. Dead again.
All right, so as you can see, it's a very complex game. It's not exactly your tic-tac-toe. It's not exactly a simple game. It's not tabular. It gets kind of similar, I'm guessing. I've never been in a person-to-person battle, but I'm guessing like the level of craziness of it might be similar. So this is the game that we've been working on. And we used some cognitive science principles like task sets, which is a notion that has been around for decades in cognitive science. And I'll talk a little bit about it. And the notion of affordances, I know some people here work on that notion as well. And some inspirations from how the prefrontal cortex analyzes these task sets in order to analyze this data. Okay, so what do I mean by large-scale data? Here's what I mean. We have the data samples that we used, they came from 57,500 full human gameplay videos. Each video corresponds to continuous gameplay by one player. Total video frames are about 1.8 billion time steps. And total hours of human gameplay is about, it's about 8,000. And here is the way that we started to, basically this is the general idea of the type of analysis that we did. For those of you who are familiar with Ila Fit at MIT, their work on hippocampus, you have been familiar with the idea of using manifolds to understand behavior of large-scale neurons. Very similar principles applied here. And in fact, Sue Sharma was a PhD student with Josh Tenenbaum and Ila Fit who did this work with me. So the idea is that we break down the kind of the analysis into task sets. Based on the task set, we have certain things that are in the fight-flight direction, some that are in the solo play versus multiplayer engagement in-game, and some of them that are in explore-exploit, because when you want to find the seeds or find the locations, you need to do all of these things. And then our goal is to not only analyze where human behavior lies, but also see what is the alignment of the AI agents with human gameplay. And I will show you the architecture of the AI very soon, but first, let's take a look at this notion of task sets. So our goal was an interpretable approach to analyzing these kinds of amounts of complex and multiplayer gameplays. I should say gameplays because it's not different games. It's the same game, but just different people playing it. And task set is one where you select a number of features. For instance, you can do a color task. You see some numbers that are typed in red or green. You can either judge what the color is, or you can judge whether the numbers are even or odd. So the fact that you are selecting the color feature or the number feature, numerosity feature, that would be the kind of task domain that you are paying attention to. And then you have an operation that you do on the domain. So it could be identify the color. Tell me if the color is blue or not. Tell me if the color is closer to green or closer to red. Or it could be, for instance, identify whether the number is odd or even. Tell me if the number is bigger or smaller than 5, or such and such. And then produce a sequence of actions to complete the task. So Sakai 2008 has this beautiful paper, Task Sets and the PFC, how the prefrontal cortex basically, different levels, different parts of the brain work together to help task sets. I apologize for the small font. Task sets are generalizable across environments. So if you can judge whether a number is above 5 or below, you should also be able to judge whether the doors on a street are above 5, the numbers of them, or below 5. And also, they are compositional. And you can see a lot of work on compositionality of task sets, especially from Michael Frank at Brown and Ann Collins at Berkeley. And affordances, we define it very simply. Obviously, it's very much inspired by Gibson's ideas from half a century ago, or maybe more than half a century at this point. Affordances is when a task set is afforded or the conditions to doing it is available, and it's the agent's choice whether to do it or not, or whether to do another task. So for instance, there is a glass of water here. It affords drinking or being drunk. I can choose whether I want to engage with this or do this other thing, which is I'm in a lecture hall, there are people listening to me. This affords me speaking about my work. So those are examples of them. As you can see, these tasks are simultaneously being afforded. And I am choosing to talk to you instead of drinking this water. So just like I mentioned, you can take a look at the affordances and look at the completions. So some tasks are simultaneously afforded. For instance, talking to you and drinking this water. Likewise, it could be attack or approach damage enemy, run from enemy in poor health, explore near enemy, etc. And once they are simultaneously afforded, then you can see how many steps from the affordance was the probability of their completion. As you can see here, this is a very scaredy agent, prefers to run, because you can see that the probability of run is a lot higher. And the probability of exploring away the near enemy is also higher. So you can tell that this is not a fighty agent, this is a flighty agent. So in that dimension of fight-flight. And so using the area under the curve of these probabilities, we can easily compare what is the agent's tendency on this axis of fight and flight. And the same thing can be done for other tasks. So you have the explore-exploit tasks, and you have the solo multitask sets. So fun fact, then you can, yes?
Just to clarify, just to understand, it's like
Yeah.
what's the sequence of like small events or something, and they're checking kind of where they are along the sequence, and then seeing from here, are they completing this sequence or are they completing that sequence or something?
Yeah, great question. So this is the time course of the game, and we have some information about the game just because of the information that's available. And we can see, okay, at this moment, these tasks were afforded simultaneously. So from here, 50 steps after, each of them like a second or 3 seconds, we framed it in different ways. So I don't know which one is this figure, but in the paper we have both 1 and 3. And then you can see, okay, from the moment this was afforded, then what was the probability of doing it? But so the entire game is long. These are just like, these are always, they're not windowed. They are time-locked to the moment of things being afforded simultaneously. So if you guys are familiar with cognitive science, it's event-based. It's depending on the moment where things get afforded. It's not time-based. And so the interesting thing is when you project some of these results into a UMAP, which is just a simple dimensionality reduction method, what you see is that reward does not shape this space. Like the reward does not make this space into 2 clear clusters. What does is the mean fight over flight area under the curve ratio. So remember, we had the area under the curve for the fight probability and flight probability with different afforded task sets. You can get a ratio of that, and you can see if somebody is fighty or flighty like me, so would run away as soon as there is a fight. And this is what you can see here. This one actually very nicely clusters this UMAP of the space, whereas the reward was not enough, and pun intended about that. Okay. So it doesn't explain this variability in behavior, basically, in the fight or flight. And just to answer your question, so this is, again, the event that is afforded simultaneously. This is simplified because we have multiple tasks that could mean attack, multiple tasks that could mean run. And you can see that, for instance, in this case, if you get the ratio of the 2, it's clear that this one is also a runny person. The other one, too. Apparently, we didn't put aggressive examples. Another interesting thing is solo versus multi. Humans are very, yes?
So in previous slide, did you try like a high-dimensional version of this like UMAP embedding?
So this is UMAP. This is a
UMAP in 2-dimensional, right?
Yeah, no, we didn't. I would love to talk about that because we have 3 general dimensions, right? We have fight, flight, explore, exploit, and we have solo multi. And we did them separately for clarity. especially since the ML community is not very much into that kinds of analysis. However, I would love to talk about that because that would be exactly the kinds of things that would be cool to do. And especially if we can find some geometry in that space, like the work that Stefano Fuzzi does at Columbia. So here, the interesting thing about solo versus multi-gameplay is that you would notice the damaged characters are more likely to engage in fight when there are other friends around. And part of this is because they get support either by somebody else joining the fight or by somebody shooting healing vibes to them and them not dying. So it was very interesting to see what determined prosocial behavior in this particular task. Interestingly, the support characters are also more likely to be at a fight scene when they have friends around because they go there and they need to shoot healing vibes at them. I can't believe I'm saying that. And then the tank characters, somewhere in between, and you can see that they're not sort of, they're also prosocial, but it's interesting here that the damage characters, the high damage characters out of the 16 personas that you have in this game are the most prosocial when they want to fight.
Sorry, can
Yeah.
I have kind of a naive question. What does the support character do in the absence in the solo play?
So there's two objectives in the game, right? One thing is protecting your territory, which has the fight and flight. Another thing is going to pick up some seeds and deposit those seeds in a location that then you have to protect as your territory. So all of them can do that. But the healing characters, they're not very good at fighting, but they are extremely good at being in a fight to help their team not lose. Yeah. And so they're very important for various kinds of fights. So, yeah.
And how big is a team?
It's a 4x4 game.
Oh, it's 4x4.
Yeah, exactly. Yeah.
So is the solo play kind of out of just like not ecologically valid in the sense that that's not how the game's normally played?
No, it is. Like I could just personally go and find some things and go drop it somewhere. I could constantly run away and maximize my distance to any kind of fight situation, and you have that kind of behavior. In fact,
I mean, like, is it actually what people do when they're playing the game for fun?
Ah, great question. So humans are not like that, but you will see why I am mentioning this so much, because the agents, in fact, they keep behaving solo. They don't show the prosocial behavior. Yeah.
They don't, maybe I'm confused about the game. They don't have to go to the other teams and find their seeds?
So let's not get into the detail. Let's just move forward. If you don't understand it, I think I'm comfortable with that. I'm worried about not making it through
what does
this
solo
slide.
play mean in the sense?
It just means you're not in a certain vicinity of other players, period. Like, I am here. I am not within a certain radius. There's no human around me, or there is no player around me.
Okay, so it is a normal multiplayer game. You're just checking, right now, there's no one else around.
Yeah.
And looking just at those times.
How much of your time do you spend when nobody else is around? How much of your time do you spend with other people, regardless of whatever you're doing?
Sorry, I thought you meant you were putting them in a completely different game.
No. Like right now, how many people are just in their office? How many people are here? Okay, yeah. No shade. That was just a joke. Okay, so what you see is that there is some affordance overlapping matrix for different tasks. We can also see in the task set space, what are the tasks that get very likely simultaneously afforded and completed close to each other when it comes to these things. So that was another thing that we did. Okay, another interesting thing, we also analyzed changes in strategy in humans. It turns out everybody after playing, regardless of their character, they switch to becoming a little bit less fighty. Because for whatever reason, even though the game affords a lot of fighting, people start to fight less, even as a damage character. We also analyzed, and I don't have it here, look at the paper, there's so many analyses there, whether it's the individual that determines how fight or flighty they are, or it's the character. Turns out it's the interaction of both. So your personality and the character you're playing interact with one another in whether you play more explore-exploity, whether you play more fight or flighty, etc. All right, let's get to the agent. So the agent is very simply, its vision is ResNet, so it captures all of the various pixels that are going on, receives it, using a ResNet-like structure, just turns them into something a lot more processable. And then that is trained on a very simple causal transformer, GPT-2-like, which has, in this case, only 222 million parameters. So this is not like 10 billion. This is not even 1 billion. Although we have trained a 1 billion, and it does better, it still is not up there in terms of the behavior. So it turns out even 1 billion was not enough. So this one is 222 million. And then there is a further layer that just translates the outcome into the specific kinds of actions you would need to take in this particular game in order to move yourself around. So data here was sampled from about 57,500 full human videos. And the training took 6 days on 6 GPUs that were V100s. You can tell this was done a couple of years ago. Obviously, we wouldn't be using V100s right now. And it was basically 72,000 steps of training. OK, so here you have the human on the top. This is for the attack versus run, for instance. And then you have the agent. And what you will observe is that the agents are basically not very much engaging with other agents, whether it's as attack or anything else. So you can see that there is a difference in the probability of completion of an attack between the two. Another thing you would notice is that if you look at this variability that we observed in humans for fight or flight, look at this for AI players. It actually is it's unclear what is going on, but they don't have any variability either with reward or with regards to, but possibly the reason is obviously that there are very few cases that they fight at all. So you don't have a lot of information here. And if you look at explore versus exploit, this is humans, explore away from the nearest seed cluster, attempt direct pickup near the seed cluster. You can see that when they're afforded, there's some variability in that, there's some preference. For AI, it's all flat. You can see that if you look at explore exploit, again, humans have this nice kind of clustering variability in the UMAP, but not the AI. AI is all over the place again, and its clustering is unclear. And maybe in all of these things, the scaling is not good. So even in that, it seems to be the case that perhaps a higher dimensional UMAP might help us to have all these 3 different axes combined with each other, or even the task sets individually and their interactions, as opposed to just the 3. OK, yeah?
I'm curious. I assume that...
the robot. The robot has a question.
Fight events are relatively rare in the play data because humans are... Have you tried upsampling them?
Great question. We tried upsampling good play in general. So there's parts of the game that somebody's just like going around or just like hanging out there or talking to their friends. There was like clipping of some of those parts, but we did not do that in particular. So I think that could be another thing that can be done. I think in the 1 billion, we have a lot more because the data that I'm showing you is 5% of the total data we have. So this is a very, even though it's giant, it's a small sample of it. So that would be an interesting thing to do. Yes, the person on, yeah. I think they can just unmute and speak.
Hi, it's Erica. I am sitting in my office solo playing because I wanted to raise the robot hand. I was wondering whether there was any difference in whether the humans or the AI agents learned sort of differentiated between the different roles, in being a healer or being a fighter, just in terms of the like signature along the 3 axes that you measured.
Yes, so I think I didn't include it in the slides. I showed this one here. Yeah, so I showed this one here in terms of the 3 types of character for humans. There is a giant figure of this that you can find the AI data as well. I think what we observed was that AI doesn't show as much role-appropriate variability in behavior as the humans were. So that's another interesting aspect of this, because you have equal parts of these characters in the training set, and they show a lot of variability in the human data that interacts with their individual user as well. But the AI was not showing as much variability. So that's another interesting. Oh.
Sorry, I muted myself, and then it wouldn't let me unmute. And
I see. Thank you. So we had a robot participation. OK. So 10, thank you. Where are we? OK, so I'm going to show you something earlier. So this is with earlier deep learning models that were cool in 2020 before the transformers happened. So take things with a grain of salt. So what we asked in a couple of papers that were in ICML was whether state-of-the-art deep learning navigation agents could pass as human-like if you observe their behavior. So this we call navigation Turing test that I will show you. We also had a diffusion model, the ICLAIR paper. If anybody's interested, come talk to me. I'm very excited about that. Instead of text-to-image diffusion, we had image-to-action diffusion, and we did sort of very fun work with that. It actually got a lot more citations than we anticipated, so I'm very happy with that, but I didn't include it in this. And so let's take a look at how we can do an interpretable analysis of 100,000 games with cognitive notions. So this was and it's not ongoing, this was published in ICML. So when I say ongoing, I mean that we want to do this also with this transform agents that we haven't done yet. So this is the game. We stripped the game of everything other than one agent just walking in the map, because obviously in this case we were interested in navigation. And this is the giant map of the place. One team starts from that side, another team starts from here. They have a skateboard, they jump over into here. It's a very kind of steampunk kind of world. And what you have here is then these different goal locations that you see. So there are multiple goal locations, in particular 16. It's a 3D video game, and the map size is basically roughly 500 to 320 meters, artificial meters. And at the time, there was this baseline paper, which was Alonso et al. In 2020, Deep RL for navigation in AAA video games. And we used that as our state of the art. So we used a symbolic agent that had a low-D representation of the game states. So it received 6-dimensional information about position and a particular goal. So very little amount of information with a bunch of feed-forward networks, and then did something. And then we had a hybrid agent that had a very simple vision, which is a very simplified version of a monochromized, cropped, and depth-only, resized image that went into visual feed-forward and a convolutional network before it went to a couple of feed-forward networks and give the output. And then we had the hybrid agent also received the symbolic, so it was combining or concatenating both the symbolic stream and the visual stream, or the convolutional neural network stream. So if we were only looking at time to goal and mean episode reward, another case of reward is not enough, it would look like they're kind of the same. They're not very different, the two agents. So if you just looked at that, that would not make a huge difference between them. However, it turns out that if you have humans try this out, they don't see them as equal. So I'm going to ask you right now to participate in the experiment. Which of these two videos do you think was played by a human? This is video 1. What is happening, internet? Oh, yeah. This is video 1. So exciting. Okay, I think it's enough. And this is video 2. We are talking about an average human player, so not a beginner. So which one is how many people think the first video is more likely to have been played by a human? How many people think video 2 was played by an average human player? Okay, video 1 was played by an average human player who does not run into obstacles and walls. Like, it does not crash its head into a wall while it's going forward. And I say average because it's not a beginner player. And so the video on the left was played by a human. All right, and the next. What about these two? And I'll play it simultaneously. Oh, maybe that's confusing. So let's watch that, and then I'll pause this. So you're watching video 1 right now. Keep this in mind. It's reaching the seeds. OK. And now you're watching video 2. How many people think video 1 was played by a human? How many people think video 2 was played? You see how much more certain you are? They were both AI. The second one was the hybrid model. So you see that if you just look at their rewards, or if you just look at the time to highest reward, they weren't different. But if you look at their behavior is actually different. So this is how we did the experiment exactly. We had humans watch, unbeknownst to them, sometimes they had a human versus agent, or they had two agents versus each other. This is how they answered the question, just like you guys, and they would say things like, oh, it was edgy, it was running into walls, it was bashing its head against things, it was running through the bushes, through the flowers. So many people said that. They were really upset at that. And we had two studies. In the first one, 30 subjects, human versus hybrid agent, 6 trials, hybrid versus symbolic, 4 trials. In the second one, we had, again, sort of the replication of this. And what we see in general is that there is agreement with the ground truth, mostly the same, whether the base agent is symbolic versus human or the base agent versus human is the hybrid. But interestingly, people are a lot overwhelmingly more likely, out of the 4 examples of hybrid versus symbolic that they see, to say that hybrid is more human. Even though when you compare the scores, whether it's AI versus human, they are equally almost good at figuring out which one is AI. But when you compare the two of them versus each other, they overwhelmingly think that the hybrid is human. In another paper, we analyzed the explanations, and this might be also interesting to Jacob. We analyzed the explanations that people gave for why they thought this is the case. Some of them had to do with movement being smooth, goal-oriented, avoiding obstacles, receptivity, intuition, etc. And we titled the paper, Navigates Like Me, because of the fact that many of them would say, this is how I would navigate if I was an average player or if I was doing things. All right, so I think that we definitely will not have time to go into detail of the second kind of part of the talk that I wanted to show you. But perhaps I can just show you a little bit of it. And then some of you have seen it. So maybe then we could see, people can talk to me. I've given this like a couple of times here to the tutorial groups. But just to be clear, cognitive neuro-inspired approaches, why would we want to do them? We know that, like, there was this kind of Microsoft ChatGPT last year saying, I want to be alive, telling someone to leave their wife and go live with them. And one of the DeepMind colleagues said, I feel a weird type of compassion for Sydney's meltdown, obviously widely inappropriate for a search engine. I can't believe I have to say that. It paints a sensitive picture of our collective wounds, infantility, and idealism. And I think this is also a slide from 2 years ago that I was reminded yesterday by Joel about it, that I think that probably some of you might find interesting. I think that LLMs offer a lens into our collective archetypes to some extent. There could be an unhelpful anthropomorphizing, but we could also use them in an analytic approach. And Adam Trischler at Microsoft Research talked about it as the cultural dark matter, which underpins so many of the stories we've told across generations. So if people wanted to use it properly. That being said, can we use cognitive science to properly evaluate them systematically? This is what I did in this paper, which was at NeurIPS last year and yesteryear. And then there is this prefrontal cortex-based architecture of LLMs talking to each other in order to improve behavior and planning. And then the neuro-inspired evaluation of the deep layers of the representations in a neuroscience-like approach. Ask me about any of them. I think I can tell a little bit about one of them. Let's maybe start with this one. We evaluated 8 different large language models using a paradigm of cog-eval with operationalization of many tasks, many prompts and graphs, and a lot of data generation with different temperatures. Tried many different of these graphs that you would see in my cognitive maps and successor representation type of work, and explained the graph in a kind of a story, either as a spatial story or as a social story to the LLM, and asked it to navigate from a node to another, which was maybe 4 steps away, 1 step away, or to choose between 2 locations of maximum reward. Overall, there were this many kinds of tasks, categorized as traversal, reward evaluation, transition, revaluation, shortcut, and detour. Long story short, all of them are pretty bad at it, including GPT-4. And for some tasks that there is a change or reversal happening, they were even worse than others. And then when you look at the ways in which, and I would have asked you if we had time, which graph do you think would be more difficult, and people usually confuse them. It turns out that this is the kind of order in which those graphs that I showed you are difficult for these graphs. meaning this little tree here. In fact, this should be kind of reversed, these two guys, because this tree turns out to be much more difficult than them. The more opportunities of choices that they have, the more mistakes they make. The longer a trajectory they have, the more likely they are to hallucinate. And when you analyze their failure modes, you see that they hallucinate edges that don't exist, they fall into loops, which should not be a part of shortest path, or they miss a shortest path and go a further way. So I'm going to stop here, but if you're interested, please come ask me. We designed a multi-agent version of LLMs inspired by the prefrontal cortex. Thank you so much. I think we're on time.